So today we are talking about discontinuities in rational functions. So we have continuous functions and discontinuous functions, right? So our polynomials are continuous from negative infinity to infinity. If I put my pencil down, I can draw the entire polynomial without picking up my pencil. Most rational functions that we're going to deal with have discontinuities. Not all of them. We'll look at a couple that don't have discontinuities. But let's talk about what those discontinuities are. All right, so they can be in the form of asymptotes. Now, we have looked at a graph that looks similar to this. We actually graphed it on our calculators. It was a little bit different, but same idea, right? And I know the fact that this part right here intersected the horizontal asymptote bothered some of you. But remember, you can cross a horizontal asymptote. You cannot cross a vertical asymptote. That affects the domain. But horizontal asymptote, you can totally cross because the horizontal asymptote is dealing with in behavior. Way out here at negative infinity, this function is approaching whatever this number is, let's say 1. And way out at positive infinity, it's approaching 1, but from the bottom. Okay? What goes on the middle, we're not really concerned with horizontal asymptotes. Vertical asymptotes does tell us what's going on in the middle. And I have to pick up my pencil a couple of times here. Okay? Here's another example of it crossing the horizontal asymptote. So this one has a horizontal asymptote at y equals 0. Right? So on the right-hand side, it looks like it probably doesn't cross it, but we don't see enough of the graph to know that for sure. But here, this one comes down, it crosses it right here, but then it still is hugging the asymptote out here at negative infinity. So the fact that it crosses it, totally fine. Okay? Another example, this one, it intersects the asymptote in an infinite number of points. But as we're getting out to the infinities, it is approaching 0. Does that make sense to you? This is called oscillating. It's bouncing back and forth. If it was oscillating really close together, like if it was squished together and bouncing back and forth really fast right here at 0 or at negative infinity, then it wouldn't be approaching anything. But that's not what's happening. It's getting smaller and smaller and approaching 0. All right, so then we can also have slant asymptotes. So in this case, I have a vertical asymptote here and a slant asymptote here. They're also called oblique asymptotes. Where are your oblique muscles? They're right here, right? There's some of your abs. You know what they help your body do? Lean over. That's why these are called slant asymptotes or oblique asymptotes. It's not a coincidence that they're named the same thing. Oblique means oblique, right? So that's what slant asymptotes look like. And you can cross a slant asymptote. On this one right here, I'm not crossing that one. But here, I'm intersecting it here, and then I come back, but I'm still approaching the asymptote when I'm way out at negative infinity. And here, same thing. Comes down here, but then it's actually approaching the asymptote out at the infinities. Okay? Make sense? We good? All right. Now here, this graph, the blue part is the function. The red part is the asymptote. So this is a parabolic asymptote. So all of your asymptotes don't have to be linear. We're not going to actually graph any functions like this, but I wanted you to see that it exists. If you were to graph this function in the calculator, all you would see is the blue part, just because that doesn't graph the asymptotes for you. But the asymptote is graphed also, so you can see how it follows that. Okay, so you can have all kinds of different asymptotes. But we're only going to look at the linear ones, but horizontal, vertical, and oblique. All right, and today should be 100% reviewed from Algebra 2. This is going on page 33 when we're done. Okay. So let's first talk about what makes a rational function a rational function. What makes a rational number a rational number? It's a number that can be written as what? A fraction, a ratio, right? So it's a number that can be written as a fraction. So 0.5 is a rational number because I can write it as 1 over 2, right? Square root of 2, not rational because I cannot write it as a fraction. Okay, we okay with all that? So a rational function means that I have to have a variable in the denominator. Most of the time we have variables in the numerator and denominator. We don't have to, but they at least have to be in the denominator. Because if I have f of x equals x over 2, well, that's written as a fraction, but I can rewrite it as 1/2 x, and that's not actually a rational function because I don't have any variables in the denominator. Does that make sense to you? So it's not just about being a fraction. It has to actually have variables down there. Okay. So most, like I said a minute ago, most rational functions have restricted domains leading to discontinuities. And our types of discontinuities are vertical, horizontal, slant, and point. which can also be called removable. Right? So we're going to start with the point discontinuities that give us holes in the graph. So point discontinuities, or holes in the graph, occur when a factor containing x, that containing x part is important, is common to the numerator and denominator. And knowing if it's common to the numerator or denominator is going to be super easy. So the first thing we do, we look at number 1. Can I just cancel out these x squareds that I see? No way, totally illegal. Can I factor something out of the denominator? Yes. So my numerator stays x squared. What can I factor out of the denominator? 3x, okay? And then that leaves me with x minus 2. And actually here, if I only factored out the x and not the 3x, it would be fine, because I can't cancel, there's not a 3 up there anyway, right? So in this case, a common factor, not the greatest common factor, wouldn't have been wrong, it would have been okay. And so then I can cancel this x with one of those, right? As soon as you cancel that, and I was able to cancel it out because x is common to the numerator and denominator, right? Whatever you cancel out, you set it equal to 0. X equals 0, and you solve it. Well, that one's already solved, okay? Then that right there, so PD for point discontinuity, once you set what you canceled out equal to 0 and solve it, that is your x value for your point, or for your hole, okay? Then my reduced function, f of x, is equal to x over 3 times x minus 2. Okay, everybody okay with that? Now I need to find the y value of the point discontinuity. I cannot substitute it into the original one. I substituted into this one, so I want f of 0, and that's going to give me 0 over 3 times 0 minus 2. And what's that give me? 0. So that is my y value there. So what you end up with is that the graph looks like this. Graph looks like this with hole here. So when you go to graph it, you actually graph your reduced function, but it has a hole at whatever your point discontinuity was. Okay? It is a hole in the graph, but is considered a point discontinuity or a removable discontinuity. Okay. Everybody good so far? Yes? Okay. Is he awake? All right. So let's look at number 2. Can I cancel out the x squareds? No, I cannot. Can I factor this? Yes. So I'm going to factor the numerator. I'm going to try to at least. Factor. So this is x. 6 is negative, so the signs are opposite. What's the positive number? 2 and a negative 3. Do we agree with that? I was doing some weird arithmetic stuff last period, so y'all keep me honest here. Make sure I don't do anything weird. Can I factor the denominator? Yes. What is this thing called? Difference of squares. So x plus 3 times x minus 3. Can I reduce this? Yes. So I can cancel these out. As soon as you cancel something out, you set it equal to 0. X minus 3 equals 0. So x equals 3. That is the x value for my point discontinuity. 3. And then we will revisit that. My reduced function, f of x, is equal to x plus 2 over x plus 3. We agree with all that? So how do I find the y value for my point? Substitute it in here, right? So I want f of 3. That's going to give me 3 plus 2 over 3 plus 3. And what does that give me? 5 over 6. Okay. Any questions at this point? Okay. Can I reduce this 2x in the denominator with one of those in the numerator? No. Okay, but can I factor something out of the numerator? Yes. And not every rational function has a whole, by the way. I don't want you to think that just because we're getting all these. So I can factor out a 2x, leaves me with an x minus 3 over 2x, right? So then I can reduce that because they are common to the numerator and denominator. So then I get that 2x equals 0, which means x equals 0. That is the x value for my point discontinuity. Right? My reduced function, f of x, is equal to x minus 3. So what's the y value? Negative 3. Now, if I was to graph this function, because that's what the function looks like, this with a hole here. When I graph this, what is this thing? It's linear, so I'm just graphing a line, right? This is how you get a line with a hole in it. Okay? So this is a line with the hole at 0, negative 3. What questions you got? All right. Let's look at vertical asymptotes. These are not new either. They occur when a factor containing x is unique to the denominator. That means you have to try to reduce it first. Okay? So when I look at number 1, can I reduce it? No, can't factor, can't do anything, right? You have a question? Yeah. Oh, shoot, maybe. Oh, shoot, I'm moving the wrong thing. I told you I'll keep me honest. On number 3, no, I'm substituting this in for x. I'm finding f of 0, and that gives me 0 minus 3. Okay? That makes sense? This is the x value that gives me this y value. Thank you for asking, because I'm sure you weren't the only one thinking that. We good on that? Okay. Don't be afraid to speak up. Stop me if I keep going. We good on that now? All right. So it's when a factor containing x is unique to the denominator. So since I cannot factor anything else, I can't reduce anything else, I definitely can't cancel those x's out. Then I take whatever's in the denominator, and I set it equal to 0. X plus 2 equals 0. So x equals negative 2. So my vertical asymptote is a line. So I have to write this as the equation of a line. It is a vertical line at x equals negative 2. So look at the differences between these two things. I set this, so when I canceled this out, I set it equal to 0, and I got x equals 0, but I didn't write x equals 0 because this represents an x value for a point. When I set the denominator equal to 0, this represents the line that is the vertical asymptote. That makes sense to you? Got to know when it's a line, you have to write it as the equation of a line. Okay. Any questions on vertical asymptotes on number 1? All right, let's look at number 2. Am I guaranteed that I have a vertical asymptote at x equals 7? No, because I need to factor it first, right? I can factor the numerator. That gives me x plus 7 times x minus 7. And then that's over x minus 7. Can I reduce this? Yes, so I reduce it, and as soon as I reduce it, I do x minus 7 equals 0. So x equals 7. What does that 7 represent? A whole. What part of the whole? The x value. Okay, so I know it didn't ask us for it, but we found it, so we're going to write it down. Point discontinuity, 7 is the x value. We will come back for the y value, but I'm also going to need to answer my vertical asymptote question. So then my reduced function is f of x equals x plus 7. So I have a vertical asymptote when there is a factor containing x unique to the denominator. What is the denominator of that function? 1, right? So I don't have a vertical asymptote, right? Because it's a line. I have a line with a hole in it again. So my vertical asymptote is none. What is the y value for my hole? 14. Good, because I'm f of 0, right? F of 0 equals 0 plus 7. What did I do? Oh, f of 7. I'm a moron. Thank you. That doesn't even, what I wrote doesn't even make sense. Is it a perfect? Oh, golly gee. I told you, I don't know what's wrong with me today. I don't even have a good excuse. Sometimes it's there's things, but I don't know. My brain is just not firing on all cylinders today. I had the correct answer at least, but I don't want to confuse you. We good? All right. So can I factor number 3? Yes. So let's factor number 3. In the numerator, I can factor out a 2, leaves me with x minus 4. In the denominator, I get x plus 4 times x minus 4. Okay. Can I reduce this? Yes. So cancel this out, and as soon as I do that, I have x minus 4 equals 0, so x equals 4. So then my point discontinuity, I have an x value of 4. I'm also going to need to answer my vertical asymptote here. So my reduced function is f of x equals 2 over x plus 4. Okay? So I take whatever factors I have in the denominator, set that equal to 0, x plus 4 equals 0, so x equals negative 4. So my vertical asymptote, I don't just put negative 4, I put x equals negative 4. Now, if you don't write this part right here, that's fine. I mean, you really should be able to look at it and know that it's negative 4, but I want to make sure you understand where it's coming from. And then if I want to find f of 4 to do that part, f of 4 is equal to 2 over 4 plus 4, 1/4. Okay. What questions do you have? Okay, good deal. So number 4 is already factored for me. Can I reduce anything? No. So in the denominator, I have 2 factors that contain x. I take both of them and set them equal to 0. X equals 0, x plus 5 equals 0. So x equals negative 5. So for vertical asymptotes, I have 2 of them, one at x equals 0 and one at x equals negative 5. These are equations of lines, so we write them separately. It's not a list of values, so I can't just say x equals 0, comma, negative 5. It's x equals 0 and x equals negative 5. I have 2 separate equations.
Right, teacher. We're going to go ahead and start.
So let's talk about horizontal asymptotes. Okay, so horizontal asymptotes occur when the degree of the denominator is greater than or equal to the degree of the numerator in a rational function. You can have 3 things going on. It can be top-heavy, bottom-heavy, or tied in degree. Horizontal asymptotes are the easiest part of rational functions. Because if it is top-heavy, so we're talking about the degree, so top-heavy in degree, that means we have the greater degree in the numerator. So if I look at number 1 here, and I look at the degrees, so I'm just looking at the greatest degree in the numerator and denominator. So here I have a 2x squared, here I have an x. Is it always going to be the first term? No. Most of the time it will be, but you've got to make sure. It's always the highest, not always the first. So this is top-heavy because the numerator has a degree of 2, denominator has a degree of 1, and so that means no horizontal asymptote. So for horizontal asymptote, since I can look at it and see that it's top-heavy, my answer is none. I don't even have to factor it to figure that out. Now, in order to do other things we need to know about rationals, we would have to factor and do some other things. But if this is all I'm being asked for, that's all I got to look at. So here on number 2, I have x third and x squared. That makes it top-heavy. So for my horizontal asymptote, that's none. We good on that? Okay. So then we have bottom-heavy in degree. So greater degree in the denominator. So when I look at number 3, I have it's 2x to the first in the denominator, really like x to the 0 in the numerator. So clearly it's bottom heavy. I have a horizontal asymptote at y equals 0. I don't even have to do any work. Horizontal asymptote, y equals 0. I look at number 4. I've got a 2x in the numerator, x squared in the denominator. That tells me it's bottom heavy, which means that my horizontal asymptote, y equals 0. Right? Everybody okay with that? There's no tricks. It really is that easy. Now, if they are tied in degree, we have a horizontal asymptote where y is the ratio of the leading coefficients. So when I look at number 5, I have a 2x and a 5x. So we are tied in degree because they're both linear. So my horizontal asymptote, it's a y equals line. It's the ratio of the leading coefficients, not the variables. It's just 2/5. So when I look at number 6, and look at this here, they are tied in degree. So my horizontal asymptote is at y equals what? 1. Okay, horizontal asymptotes, super easy. Just make sure you know the difference between top heavy, bottom heavy, and tied in degree. And if you always say them in that order, then you can kind of remember them in that order. It's not that big of a deal. Okay? All right, slant asymptotes. Slant asymptotes, which also could be called oblique. Let's write that word out here. Could be oblique, O-B-L-I-Q-U-E. They occur when and we're going to pick out the word reduced. The rational function contains an x in the denominator, and the numerator is 1 greater in degree than the denominator. If it's more than 1 greater in degree, like if it's 2 greater in the degree, that's how you get your parabolic asymptote, and so forth and so on. So we're only worried about the 1 greater to get the lines. And it's found by dividing the numerator by the denominator. So we do want to reduce it, even though it doesn't have to be the reduced rational function that has an x in it. We want to reduce it because that makes everything a little bit easier along the way. So when I look at this, I'm going to try and factor this. Right? So in my numerator, I'm going to have x and x. 3 is positive, so the signs are the same. X minus 2 in the denominator. What are my 2 numbers that go in the numerator? 1 and 3. So can I reduce this? No. All right, but since this is top heavy, that means I do not have a horizontal asymptote. But I do have, but I'm going to have a slant asymptote. And in order to figure that out, I need to divide. But when I do that, I do not want the factored form. Like I needed to factor, because if I could reduce, I want to reduce. But now I need to divide. And so if I take this right here and I divide the numerator by the denominator, can I use synthetic division? Yes. So let's use synthetic division. And we've got 2 on the outside. I'm not. 2 on the outside, then 1, negative 4, and 3. So I bring down my 1. This is 2, negative 2, negative 4, negative 1. Okay. So my slant asymptote is a line, so it is y equals. And what does this right here give me? X minus 2. And then when we have, when we're finding slant asymptotes, we expect to get a remainder. If we don't get a remainder, we did something wrong or we didn't reduce it yet. And for the line, we don't even care about the remainder. We ignore it. We're going to talk tomorrow about what the remainder means because it does tell us something, but that is how we find the equation of the line. That's your slant asymptote. Okay. We good so far? How did I know to divide it by 2? To divide what by 2? Oh, right here? Yeah, from there, okay. Does that make sense? All right. Then let's look at number 2. Can I cancel out this 2x with one of those? No. But I can factor. So in the numerator, I can factor out a 2x, leaves me with x minus 2. Denominator is 2x. Right? Then I can reduce it. Cancel those out. As soon as I cancel something out, 2x equals 0. which means x equals 0. Yes? So we just found a point discontinuity, so we're going to write it down. That x value is 0, and then I'm also going to have to answer the slant asymptote question. So my reduced function here, f of x equals x minus 2. All right, so I take the numerator and divide it by the denominator, and what do I get? What's the denominator of that function? 1. So what's x minus 2 divided by 1? X minus 2, right? It's just x minus 2. So the slant asymptote, and this is where things get a little weird, is y equals x minus 2. If your reduced function is a linear, then the line is its own slant asymptote. And I will kind of explain to you why that is tomorrow, and I know that seems weird. Sometimes it's taught as there isn't one, but technically there is one. It's just the exact same thing, okay? And like I said, we'll talk about that a little bit more tomorrow. But then I need, what would my y value be here for the point discontinuity? -2, good. All right, any questions about that? Except the y, and we'll get to the y tomorrow. We're good? All right. So on number 3, the numerator is probably factorable. I don't know, I haven't even tried. But even if I factored it, I'd factor it into 2 binomials, right? And if I factor it into 2 binomials, are they going to cancel out with the 2x? No, and that's all I'm worried about doing right now, so I don't even care if it factors, right? So I don't even need to. So this, since I don't have the binomial, I'm not going to use synthetic division. I'll have to use long division. So I've got 2x on the outside. On the inside, I have 2x squared minus 4x plus 3. All right. So 2x squared divided by 2x is x. So this gives me 2x squared plus, wait. Oh yeah, sorry, plus nothing. Duh. 2x squared, that's all I get. And then I change the sign. Those cancel out, bring down my negative 4x. So then I get a negative 2 right there, right? That gives me negative 4x. Change my sign and get 0. And then this is going to give me my remainder. So really once I get to that point, I don't have to finish the whole thing. So my slant asymptote is that y equals x minus 2. Now I'm going to show you a different way to think about it, which may confuse some of you, but some of you that get this stuff a little bit more, it's something so you wouldn't have to do that. But I'm going to show you the why behind it first. Since this is a fraction with 3 things added, I can separate it into 3 fractions, right? I can separate it into 2x squared over 2x minus 4x over 2x plus 3 over 2x. Do you agree that that's the same thing? The common denominator, if I added them back up, I'd get that right back, right? So then if I reduce each one of these, 2x squared divided by 2x is x, negative 4x over 2x is minus 2, and then I have this remainder. You see how this is the same thing as what we got over there? And you don't even have to write it out like this. I'm writing it out like that so you can see it and understand it. But here's what you can kind of do is just from here. 2x squared divided by 2x is just x, and negative 4x divided by 2x is negative 2. So that's where you get your x minus 2 from. It only works if the denominator is just one term, okay? And that's just kind of a shortcut to do that. Like I said, if that makes sense to you and you know you can use it without making up math, knock yourself out. If you're like, I'm not sure what you just said and I'm afraid I'm going to confuse myself, do long division. It won't kill you. Okay? We good on that? All right. So now let's look at number 4. So just in the so let's look at the numerator here. And if I wanted to factor this, so let's just think without actually doing and look at the numerator. If I factored this by grouping, I could factor out a 2x squared, right? Leaves me with x minus 2. And can I factor anything out of this part that will leave me with x minus 2? No. So can I factor the numerator by grouping? No. Do you know how else to factor something with 4 terms right now? No. So I'm just going to tell you right now, nothing's going to cancel out. Okay? So just to save us some time here. So nothing's going to cancel out. I need to find my slant asymptote. Can I use synthetic division here? No. So I'm going to have to use long division. So I'm going to have x squared plus 2x minus 1 divided into 2x cubed minus 4x squared plus 9x minus 7. All right, so 2x cubed divided by x squared is 2x, right? So then this gives me 2x cubed plus 4x squared minus 2x. And then I'm going to change the signs. Those zero out. Do these zero out? Nope. Negative 8x squared plus 11x, and then minus 7. So then negative 8x squared divided by x squared is negative 8. Do I need to go any farther? No, because the rest will give me my remainder and whatnot, right? Do I care about that? No, as long as I'm confident that that is the right number, then I'm good, and my slant asymptote is y equals 2x minus 8. And I'm done. Okay? What questions you got? We good? Where's your assignment? Delta Math. Do it. All right? And go ahead and get this taped in. When the bell rings, where are you going? Math time.